Okay, so this is your quiz review for square roots and for simplifying expressions. So if you see at the top of this paper, I added in all the perfect squares up to 12 times 12. So the first set of directions ask you to estimate these square roots. You're not supposed to use a calculator to do this, so what you're really looking to do is determine where this square root that you can't do very easily falls between in terms of these numbers up here. So you can see this one is between 16 and 25. The square root of 16 is 4, and square root of 25 is 5. So this answer to this is somewhere between 4 and 5. So I know this much. The answer is between 4 and 5. And you don't always have to write it out. I'm just doing this first one like this for sort of illustrative purposes. So if I think about it this way, 20 is 4 places away from 16, and it's 5 places away from 25. So it's very close to being right in the middle, but it's actually just a little closer to 16. So in other words, it's a little closer to 4. So I would call this one 4.4. Square root of 79 is just short of 81, so we know that 81 is 9. Square root of 81 is 9. The square root of 79 must be just a little less than 9. I'm going to go 8.9. Square root of 102 is just a little bit more than 100. So here again, I know 100 square root is 10. I'm thinking 102 must be just a little bit more than that, maybe 10.1. I guess I'd take 10.2 there also. And over here, I'd probably take 8.8. And here, I'd take 4.5 as an acceptable answer. If we keep going, though, now we have a whole bunch of estimating square root problems, some of which are a little easier than others, but we have a pattern to these problems. Mr. Bryson, if you're in the building, please call the office. Mr. Bryson. The pattern is, if you look at number 4, you see you have one big square root. That pattern is to turn it into 2 separate square roots. If you notice, that's going to be the same thing you do with number 7, and the same thing you do with number 8. Because they're all just one square root trying to turn it into 2 to simplify it. So number 4, we have square root of 300. What I'm looking for is the biggest perfect square. It has to be a perfect square, and you definitely want the biggest one possible. So in this case, the biggest one of these numbers that divides into 300 is 100. And it would be 100 times 3. The reason I do this is because I can actually do the square root of 100, which is 10. And the square root of 3 I can't do, but at least it's smaller than the square root of 300. And don't forget this had a negative in front of it, so I just bring that negative down and put it there. Okay, I look at square root of 80, and I'm thinking the same idea. Which one of these numbers up here divides evenly into 80? I think that number is going to be 16. And it's 16 times 5. So I can do the square root of 16, that's 4, and the square root of 5 is left over. Now I'm down here to 162, and again I'm looking for the biggest one. I think 9 would go into this, but that's not big enough. Actually, 81 is the biggest square root that goes into this one, perfect square. 81 times 2. Square root of 81 is 9, and the square root of 2 is left over. The second pattern of problem I'm looking for is the kind where I already have 2 square roots, and these usually tell you they want you to multiply it back together into 1 square root instead. And that's the same thing I see here in number 10, another problem where I have to multiply it back to 1 square root. So I'm going to do 6 times 24. You can use a calculator if you want, or if you don't need to. 6 times 24 is 144. It turns out that 144 is a perfect square. This answer is 12. For number 10, 5 times 85, that's a little tougher. 5 times 80 is 400, and 5 times 5 is 25, so this is really 425. Now I've got to find one of these numbers up here that divides evenly into 425. That's probably work for a calculator. So what I would do is I take my calculator and I start with the biggest numbers and I keep going down until I find one that divides evenly into it. So 425 divided by 144, that gives me some decimal, that doesn't work. 425 divided by 121, another decimal that doesn't work. I know 100 doesn't divide evenly into it. How about 81? 425 divided by 81. Nope, still a decimal. 425 divided by 64. Still a decimal. 425 divided by 49. A decimal. 425 divided by 36. A decimal. 425 divided by 25, that ought to work. 17. That's the biggest one, so even though we went all the way down to 25, it turns out that 17 and 25 work. So I can do the square root of 25, that's 5, and I have to leave it with 17. So sometimes when you multiply them back together like this one, number 5, it worked out nice and easy that we had a perfect square. But in the case of number 10, we got a big number, it's not a perfect square, so instead, I look at that big number and I say to myself, look, that probably isn't correct, finalized, so maybe I have to split it, and that's why I went to this rationale. So occasionally you have to put it back together so you can re-split it the correct way. If you look at the beginning problem, it wasn't split right, because neither one is a perfect square. That's why we had to multiply it back together and then re-split it the proper way. Okay, the last pattern I'm looking for with these kind of, sort of, basic square roots is fraction ones. Fractions work two ways. Either they can start out as two separate square roots, like this one, and then what I want to do there is usually turn it into one big square root, like this. And if they're already one big one, most of the time it's better. If you can't simplify under here, most of the time it's better to turn it into two separate square roots like this. The problem kind of leads you in the direction it wants you to go. All right, so if you look at number 6, I want to take this and simplify the fraction. 72 divided by 2 turns out to be 36, and that is just 6. Down here, when I put it into two square roots, now I can see that square root of 9 was an easy square root, but I still have the square root of 50 on top. That could be kind of a pain, but I'm going to treat it as if this bottom part isn't even here for the moment. I'm just going to focus on the square root of 50. And I'm going to treat it just like I did number 4, or number 8, or number 10. I'm sorry, number 4, number 8, or number 7. And I'm just going to try to split 50. The biggest one of these that goes into that is 25. So what I really have here is the square root of 25 times the square root of 2, all over 3. And then my final answer, because square root of 25 is 5, square root of 2, all over 3. Obviously the toughest one on here. A little tricky, but really not that bad if you work it in parts. Okay, this time we have square roots where the directions tell us again we have to simplify, but I think this time we're going to probably have to rationalize. Which, like I said before, is a last resort method, but sometimes it's the only way. You never want to leave a problem with a square root in the base like that. So for this one, rationalizing means to multiply the whole thing by the square root of 3 over the square root of 3. In the denominator, that's going to just give us 3. And on the top, we get 2 and square root of 3 multiplied together. You can't take a regular number and multiply it by a square rooted number. So all you can really do is just write 2 square root of 3. I look at it one more time to make sure I can't simplify the square root, which I can't, and I can't simplify this fraction anymore, so this is done. For number 12, I see 2 square roots here, one on top of the other. So if I look back to number 6, for example, when I saw that, I put it as one big one to see if I could simplify it. That would be my first thought process. But I look at that and I say, if I were to make it one big square root, it would be 32 over 5, and that really doesn't simplify. So going that method doesn't really help. So unfortunately, I'm stuck rationalizing again, and this time it's square root of 5 over 5, so that on the bottom, I just get the 5. On the top, I have 4 square root of 32 and square root of 5 to multiply together. But I can't put this 4 times this other stuff. But I can do 5 and 32 because they're both under the square root. That leaves me with 4 times the square root of 160. So I see that square root of 160 there, and it makes me think right away that's an awful big number to leave as a finalized square root answer. So I want to look at that and see if I can't maybe split that up into a smaller square root like we would have done before. So it's a pretty big number, so maybe I go back to my calculator again. I know 100 doesn't go evenly into that, and I know 81 doesn't either. 64? I don't think so, but we can try it. No, that's a decimal, it's 2.5. 160 divided by 49, I don't think that works either. No. 160 divided by 36, no. 160 divided by 25, no. 160 divided by 16, there we go. That works 10 times. So I've got 4 on the top, and then I've broken this square root into 16 and 10. This is all over 5. So I got 4, and then I got square root of 16, which is also 4. And I can't do anything with that. So I got 4 and times, really, what is 4 again? So 4 times 4, that's just 16. And then I got the square root of 10 left over, and that's still all over 5. And finally, done. Here again, for number 13, I see 2 square roots, one on top of the other, and I'm thinking to myself, what if I make it one big one? Can I reduce it or simplify it? Again, it would be 5 over 7, and that really doesn't reduce or simplify. So I'm stuck with rationalizing one more time. So I'm going to get on the top, remember I can multiply stuff under a square root together or things outside of the square root together, but not both at the same time. So this is going to end up being 3 square root of 35 all over 7. Well, 35 isn't too bad, but I want to check it anyway. If I look at it, 25 obviously doesn't go into that, neither does 16. 35 divided by 9 doesn't work. 35 divided by 4 doesn't work. So actually, there are no perfect squares that go into 35 evenly, so we'll have to leave that. And I can't reduce 3 over 7, so this is actually done. Now we're down to adding and subtracting, kind of the last part of square root. So ideally, you get a problem where adding and subtracting is easy because you have the same number under the square root. So I'm just saying 5 of these plus 3 of these, that's just 8 square root of 2. That's the perfect situation. Sometimes, however, that doesn't come up. Like in number 15, I have square root of 80, and then I have something with a square root of 5. I can't subtract those as they are, but I think I might be able to do something with that square root of 80. But this, square root of 5 is as low as it goes. So this part, I'm just going to leave kind of by itself for a minute and work on the square root of 80, see if I can simplify it. So I'm looking at which one of these numbers goes into it. The biggest one, I think, is 16. So I'm going to do 16 and 5, and I still got this 5 square root of 5 over here. Square root of 16 is 4. Square root of 5. And I got minus 5 square root of 5. Well, so now I got something I can subtract. 4 minus 5, that's negative 1, or just negative square root of 5. So see, what happens is usually you can actually subtract them or add them. It's just sometimes you have to simplify it first so that then you can do the subtraction or addition at the end. So if you look at this one, I got a square root of 12 and a square root of 27. Actually, I think both of them can be simplified first. So let's work on square root of 12. Well, the only number that goes into that is 4, so I got square root of 4 and square root of 3. That's going to give me 2 square root of 3. Now I got 7 square root of 27. So square root of 27, it looks like 9 goes into that one. So I got 7, and then I got square root of 9, square root of 3. Now square root of 9 is equal to 3. So I have 7 times 3 times the square root of 3. That's 21 square root of 3. And I put it together to get 23 square root of 3. Square roots are such a kind of tricky thing. The idea is that never is there really only one way to do a problem, although most of the time there's a shorter, easier way than other ways, especially when you have to do this rationalizing stuff. You always want to check to see if there's a faster way of doing it, as long as that faster way is actually mathematically correct. In this case, we actually had to rationalize all three of these. There was no other way to do it. But if you get one that looks like this, in number 6, you could actually go through and multiply by the square root of 2 over the square root of 2, and then you have to simplify the top of it, simplify the bottom, and divide the fraction to finally get down to 6 as an answer. But instead of doing all that, you could make it one square root and do what we did. So ideally, this is what you want to do for the problem, but it only helps you if that simplifying is actually possible. So when we go back to this stuff again, the idea is overall, let's try to find the easiest way to do it. Mathematicians are kind of lazy usually, so we always look for the simplest and easiest way to do things, but that's the whole point of simplifying. Okay, so we're taking a little bit of a switch in gears here to go from square root into simplifying expressions. And we start simplifying expressions with some of the things we did in class already, which are word problems turned into algebra. So this one says the number of slices of bread in L loaves if there are 15 slices per loaf. So I would think of that as, well, okay, I don't know what L is, but let me make up a number for it. If I make up a number, let's call that 2. Okay, well, if I have 15 slices per loaf and I have 2 loaves, then I would be saying 15 times 2 to give me my answer. And see, the problem is I don't know that it's 2. All I know is that the number that should be there is an L, a variable. So really, this algebra expression is the same thing, except I replace where I put that hypothetical 2 with an L, 15L. Number 18, same rationale. The distance remaining after m miles of a 400-mile race. So if I said, okay, I've gone 30 miles, well, my 400-mile race, how much do I have left over? Well, I would be doing 400 minus 30. But see, I don't know that it's 30. All I know is that it's m. So this just helped me to write it so that I could figure it out with numbers. But I want to set it up so I can figure out with any number of miles, not just 30. So I just replace the 30 with the variable. Number 19, a little bit more tricky because you have multiple variables. But it says total. As soon as I see total, usually I'm thinking add. So I'm talking about a number of points scored by a basketball player after he has F free throws, B 2-pointers, and C 3-pointers. In other words, add up all the possible shots that this person made and give me a total point value. So let's say I made 2 free throws, 3 two-pointers, and 4 three-pointers. I would look at that and say, okay, I know free throws are worth 1 point, so I got 2 points from that. I got 3 two-point baskets, so that's 6. And I got 4 three-point baskets, which is 12. And that's how I would get my total out of that. But the problem with that is that it doesn't really show you exactly what you did. What I really did was take 2 times the number of free throws, so that's 2F. But see, free throws are only worth 1 point, so I don't really need a 2 there. What I actually need is not how many free throws, because I just made that up. I want F free throws. And I'm not going to multiply them by anything because it's just times 1, right? 2-point shots, I had 3 of them. What I did was I took 3 and multiplied it by 2. Again, I don't know that it was 3. I know that I can just write a D there, though. I'll say 2 times D. And for three-pointers, instead of 4, because I didn't know it was a 4, I'm going to use C. I just did 3 times C. And finally, for number 20, we're talking about the total cost of a membership with a one-time fee of $50 plus a $10 per month fee after M months. So I'm looking at my total cost, and I'm saying, how much do I actually pay? So what if I did like 2 months? Well, I have to pay $50 to start, and then I'm going to give them $10 per month, but I'm going to use for 2 months, so that's $20. So what I really did was I took $50, and then I added 20, but I got the 20 by saying 10 times 2. But I don't know it's 2. I want to write it for any number of months. So really this is 50 plus 10 times M. You can think of that situation, it's called a linear relationship. It applies to a lot of different things. Most of the time, anytime you have monthly payments on something, they often ask you to put a down payment down. For example, if you buy a car and you have to pay $3,000 down and then pay $400 per month, the algebra equation for that would be very much the same thing, except it would be 3,000 down plus 400 per month. That represents what you pay for a car. That's just like a real life example for you, since sometimes we like to do that in algebra. Let's keep going. All right, these are simplifying expressions. What I suggest, evaluating expressions. What I suggest for this is if you're going to use a calculator, a lot of students like this, you're going to use a calculator. Anytime you substitute a number in, put that number in parentheses where the variable was. So for this first one, I'm going to do 6 times 1 minus 3, and B is negative 2. So I put that negative 2 there and then square. And C is 4, again in parentheses. So if you type that exactly how it's written right there in the calculator, you would get your answer. But the trouble is that a lot of people don't put the parentheses in, and then the calculator gives them a very strict order of operations answer, which isn't always what you intended. So I'm going to avoid the calculator and work it out myself. 4 cubed, that's 4 times 4 times 4. That's going to give me 16 times 4, which is 64. Negative 2 squared is positive 4, times negative 3 is negative 12. 6 times 1 is 6. I'm just going to put all that together. What I really see is positive 6, positive 64, that's 70, minus 12 gives me a grand total of 58. We'll do the exact same thing over here with this one. Yeah, I think it actually takes longer to enter it into the calculator than it does to just work it out yourself. 1 squared is 1 times 3 is 3 times negative 2 is negative 6. 4 cubed we said was 64 times negative 1 is negative 64. And then plus negative 2 really to me means minus 2. So I got negative 70, negative 72. E squared minus 4ac over 2a you're going to learn later on is part of the quadratic formula that we use to get a lot. So here we go again, just substituting with parentheses. These problems become very redundant after a while. If you can do one, usually you can do them all. So I've got negative 4, or negative 2 squared, that's positive 4, minus 4 times 1 times 4 is 16, all over 2. What I really got is negative 12 over 2, and that's negative 6. Evaluating doesn't seem to be something that's too terribly difficult. Most of the time it's mistakes with negatives and stuff like that. Down to the last part, which is simplifying expressions. Simplifying expressions really isn't too bad either. It's just combining like terms. So I'm looking at this and I'm thinking to myself, okay, I'm looking for any kind of terms with x's in it. I got a negative x here and a positive 4x here. I put those two together and I got 3x. That takes care of that and that. Here's two y terms, negative 3 and negative 9. That's negative 12y. Takes care of that and that. And I got a positive 2, so plus 2 on the end. Takes care of that. Number 25 has a little trick in it that people tend to mistake. When you got a negative outside here, or a minus sign out here, really you can treat it like a negative 1. So I'm going to leave this 5 alone for a minute, and then I'm going to distribute the negative 1 to all of this. Negative 1 times 3m is negative 3m. Negative 1 times 2n is negative 2n. Then I got a plus 6n on the end. I'm going to clean it up a little bit. I see negative 3m with no other m's in here, so negative 3m. Care of that one. I got a negative 2n and a positive 6n. That's positive 4n. Care of that and that. And then I got a positive 5 as a final answer. Last two. So number 26 is just trying to incorporate everything you can think of into one of these problems. So we have a negative 4 out here. We're going to take that negative 4 together, the whole thing, and multiply it by each one of these. So I actually have positive 4a and negative 12b. And here again, this minus sign here actually works with the 3. It's a negative 3 times both. So I got negative 3a and positive 15b. Put some like terms together here. 4a negative 3a gives me 1a, or just a. And negative 12b and positive 15b gives me 3b. So you can see when it comes to simplifying, that original problem, all that stuff, reduces down to just a plus 3b. Clearly much more simplistic than that beginning problem. Here we are with a variable times parentheses. Still really the same thing. X times 4, that's just 4x. And x times y, you can't do anything with it other than just say xy. Here again, a negative, not just minus, but negative 2x times each one. That's going to be negative 2xy and negative 14x. So I see 4x and negative 14x, that's negative 10x. I see positive 1xy minus 2xy, that's going to leave you with negative 1 or just negative xy. All done. Okay, so that's your whole review. If you have any questions, you can come and see me in the morning during homeroom. We're also 6th or 7th period or free period. And because this test is going on during 3rd and 5th period, if you have me 8th period, you can also see me in one of those classes. I can't really help you a whole lot, but I could probably talk you through a little bit of it during then. Don't forget, you have a big surprise coming tomorrow. I think you're going to like it.